Right now, somewhere above North Dakota, a missile is being tracked. Not a real one, a simulation, but the system tracking it, the radar arrays, the supercomputers, the interceptors in their silos, those are completely real. The United States has spent $350 billion since 1983 trying to answer one question. If a nuclear missile were launched at an American city, traveling at 15,000 miles per hour through the vacuum of space, could we stop it? For 40 years, the answer was maybe. In 2025, the United States announced the Golden Dome. $175 billion, a complete layered shield over the entire country, space-based sensors, ground-based interceptors, AI-driven tracking, kill vehicles that hit a bullet, with a bullet, in the vacuum of space. This is the most ambitious defense engineering project in human history. And this is exactly how America is building it.
Welcome to full-scale manufacturing. Today, we enter the world's most complex factory to build the future of power.
The Golden Dome is not one system. It is 6. Each layer designed to intercept a nuclear warhead at a different point in its flight path. Layer 1. Space-based sensors. Satellites in low Earth orbit detecting a missile launch within seconds from the infrared heat signature of its rocket plume before it even clears the atmosphere. Layer 2. Boost phase interceptors. Missiles or directed energy weapons designed to destroy the attacking missile while its own engines are still burning when it is largest, slowest, and most vulnerable. Layer 3. Mid-course defense. The GMD system, ground-based mid-course defense. 44 interceptor missiles buried in silos in Alaska and California, designed to launch into space and destroy a warhead traveling at 15,000 miles per hour in the vacuum of space, using only kinetic energy. No warhead, no explosion. Pure impact. Layer 4. Terminal high altitude. THAAD batteries, Terminal High Altitude Area Defense, positioned to intercept warheads that survive the mid-course layer as they re-enter the atmosphere. Layer 5. Aegis Missile Defense. Navy destroyers and cruisers equipped with SM-3 missiles, providing mobile coverage across the oceans. Layer 6. Patriot and SHORAD systems. Final close-in defense for specific high-value targets, the last line before impact. Each layer has a probability of intercept. Layer 1 alone might stop 30% of incoming. Layer 1 plus Layer 2, perhaps 55%. Stack all 6, and the probability of a single warhead reaching an American city approaches 0. That is the theory. $175 billion is the cost of testing whether the theory is correct, without ever having to find out the hard way. The Golden Dome requires power on a scale that challenges the electrical grid. The phased array radars that track incoming warheads, each one consumes between 2 and 6 megawatts of continuous electrical power. The United States currently operates 17 major radar installations as part of its missile defense architecture, running continuously, 24 hours a day, 365 days a year. You do not turn off missile defense radar because it is expensive. The power infrastructure supporting these systems is itself hardened. Underground cables, independent generation facilities, multiple redundant feeds, because a missile defense system that loses power when it is most needed is not a missile defense system. The computing requirement is what most people do not appreciate. An intercontinental ballistic missile travels at Mach 20, 15,000 miles per hour. From launch in North Korea to an American city, it takes approximately 33 minutes. In those 33 minutes, the tracking computers must detect the launch, classify the threat, calculate the trajectory, predict the impact point, select the intercept solution, launch the interceptors, guide them to the target, confirm kill or redirect. All of this in under 20 minutes, because the interceptors themselves need 13 minutes to reach intercept altitude. The computing systems that do this operate at petaflop scale, 1 quadrillion floating point operations per second. They are cooled with liquid nitrogen, because at these processing speeds, conventional cooling is simply not enough. The servers are hardened against electromagnetic pulse, the phenomenon that accompanies a nuclear detonation, which destroys conventional electronics within hundreds of miles. Because a system designed to stop nuclear missiles that is destroyed by the electromagnetic pulse of the first one has failed at its most fundamental requirement. The GMD Interceptor, the missile that goes up to destroy the incoming warhead, is one of the most precisely engineered objects ever manufactured. It weighs 13,000 kilograms at launch. By the time it reaches intercept altitude, it weighs 64 kilograms. Everything else has been burned as fuel. What remains is called the Exo-atmospheric Kill Vehicle, the EKV, a guided impactor the size of a trash can traveling at 10 kilometers per second that must hit an object the size of a small car, also traveling at 10 kilometers per second, in the vacuum of space, with no air to stabilize either, using only onboard sensors. The kill vehicle contains an infrared seeker, sensitive enough to detect the temperature difference between a nuclear warhead and empty space, which is approximately 200 degrees Celsius, at a range of 300 kilometers. The guidance computer makes 1,000 course corrections per second in the final approach phase. The silo that holds the interceptor is machined from high-strength steel to tolerances of 0.5 millimeters across a structure that is 21 meters deep and 2.5 meters in diameter. The pressurized launch system, a cold gas ejection mechanism, accelerates the interceptor from 0 to 60 meters per second in under 1 second, before the rocket motor ignites above the silo, protecting the underground infrastructure from the rocket exhaust. Loading an interceptor into its silo requires 72 hours of careful operations, precise alignment, connection verification, seal testing, because an interceptor that fails to launch when commanded is not a malfunction. It is a city that was not defended. The people who operate the Golden Dome do not work in conventional buildings. They work underground. The Missile Defense Operations Center, the facility from which intercept decisions are made, is buried under reinforced concrete and earth, designed to survive the detonation of a nuclear weapon at the surface above it. The blast doors weigh 25 tons each. They close in under 30 seconds. The facility has independent power generation, independent air supply, independent water supply, capable of sustaining operations for 30 days without any external support. Because the scenario in which missile defense is most needed is also the scenario in which the surface above it may not be survivable. The operators inside, typically a crew of dozens of specialists, monitor global airspace on screens showing real-time tracking data from every sensor in the network. A ballistic missile launch anywhere on Earth appears on their screens within 15 seconds of liftoff. 15 seconds. The decision to launch an interceptor, the most consequential military decision that can be made in peacetime, must be authorized through a chain of command that reaches to the President of the United States. And it must happen in under 5 minutes. The operators train for this decision every day. Simulations, scenario exercises, protocol drills. because on the day it is not a simulation, there will be no time to practice. The life support systems in these bunkers are engineering marvels in their own right. Air filtration rated for nuclear, biological, and chemical contamination. Water recycling at 95% efficiency. Emergency power generators with 90-day fuel reserves. The people inside these facilities are prepared to operate in complete isolation for as long as necessary to ensure that the missiles above them continue to fly. The radar systems of the Golden Dome are the eyes of the shield, and they are extraordinary. The AN/TPY-2 radar, the primary tracking radar for terminal defense, is a phased array system with 25,344 individual transmit-receive modules. Each module is the size of a brick. Together they form a panel approximately 9 meters across. Together, they can track a basketball-sized object at a range of 1,000 kilometers. The radar does not use a rotating antenna. It electronically steers its beam, pointing anywhere in its coverage hemisphere in under 1 millisecond. At full power, it transmits 2.5 megawatts of radar energy, enough to blind conventional electronics at close range. The Aegis radar system, aboard Navy destroyers, adds mobile coverage across the oceans. A single Aegis-equipped destroyer can track 100 targets simultaneously, while simultaneously guiding interceptor missiles to multiple targets. Simultaneously. The seeker head of the kill vehicle, the infrared detector that guides the final intercept, is cooled to minus 196 degrees Celsius, the temperature of liquid nitrogen, because at room temperature, the infrared detector would be blinded by its own thermal emission. The target it is looking for, a nuclear warhead in space, radiates about 200 degrees of heat above the background of empty space. The seeker must detect that signal at a range of 300 kilometers while traveling at 10 kilometers per second through the vibration of its own thrusters, making 1,000 guidance corrections per second.
To hit something the size of a car. The people who designed the system spent 40 years getting it right, and it still only works most of the time. That is the honest answer to the $175 billion question, most of the time. Which means the best missile defense is still not needing to use it.
The Golden Dome is not the first time America has attempted this problem. In 1983, President Reagan announced the Strategic Defense Initiative, nicknamed Star Wars. The concept was simple. Use space-based weapons, lasers, particle beams, kinetic interceptors, to destroy Soviet missiles before they reached American cities. It never worked. The physics was sound. The engineering was not ready. The computers of 1983 could not process the tracking data fast enough. The sensors were not precise enough. The interceptors were not reliable enough. $30 billion spent. Program canceled in 1993. What changed? Between Star Wars in 1983 and Golden Dome in 2025 is everything. Processing power increased by a factor of 1 trillion since 1983. Sensor technology advanced by decades. Interceptor reliability improved from less than 50% to over 85% in recent tests. The space-based layer, the component that Reagan could not build, is now technically feasible. SpaceX has demonstrated the ability to launch hundreds of small satellites for the cost of a single large one. The Golden Dome's space layer would deploy thousands of sensors and potentially interceptors in low Earth orbit, providing global coverage that no ground-based system can achieve alone. The technical challenges that remain are significant. Discriminating real warheads from decoys, Sophisticated adversaries deploy dozens of decoys alongside each real warhead. The system must identify the real one. Managing space debris from intercepts. A successful intercept in low Earth orbit creates thousands of fragments, each one a hazard to satellites, potentially including the defense satellites themselves. These are not solved problems. $175 billion is the investment in solving them. Whether it works will not be known until the day it is needed. And on that day, if it works, no one will ever know, because the missiles it stopped will simply never have arrived. That is what success looks like. Silence, safety, and a shield no one ever had to see work.